just want to maybe put things in perspective for everybody. We've had a lot of numbers floating around. For instance, as David was saying, we have in the early universe only one extra matter particle for every billion antimatter matter pairs. So what does 1 in a billion look like? I think big numbers, 1 in a million, 1 in a billion. All right, let's start with 1 in 1,000. If that 1 in 1,000 is finding 1 millimeter in a meter, or finding 1 second in 17 minutes. So imagine waiting 17 minutes and you just have to find that 1 second. So let's go up a couple orders of magnitude. 1 in a million, now we have to find 1 millimeter in a kilometer, or 1 second in 12 days. And so we were talking in the billions here, our ratio. 1 in a billion would be like finding a millimeter in 1,000 kilometers, or 1 second in 30 years. So visually, from our lab, if we go out a kilometer, we're in the middle of Pacific Spirit Park, we'd have to find 1 millimeter in here. So 1 in a million. 1 in a billion, we would get all the way up to Saskatchewan, we'd have to find that same 1 millimeter. So this is, the rarity that we're looking at these particles. In time, again, 12 days, that would take us out to February, so next month from today, we'd have to find 1 second for the ratio to be 1 in a million. 1 in a billion, we're gonna have to wait 30 years. So picture waiting all the way until 2047, and all you're doing is trying to find 1 second that's special. So that's how rare that extra matter particle was compared to all of the pairs of matter, antimatter. So antimatter comes from all around. We were saying cosmic rays will produce antimatter. About 0.02% of particles from cosmic rays will be antimatter. And in a square meter, anywhere on the Earth, at any point in time, there's approximately 1 to 100 antimatter particles being produced at any given time. So antimatter is all around. You can even find it in your kitchen. So potassium-40 is radioactive and will decay at the rate of about 1 positron every 75 minutes or so. But don't worry, it will annihilate with an electron. It's not that big a deal. But just the fact that it is around, we can actually measure these things. So how much does it cost to produce? 1 millionth of a gram of antimatter costs about $60 billion US. So how can we picture that? All right, here's $1 billion. All right, we have 10 crates of $100 bills stacked up, and so we need 60 of those. All right, and that's to get to 1 millionth of a gram of antimatter. This is the cost of running our accelerators and how long it took to develop the programs. To put this in perspective, the actual Manhattan Project only cost about $26 billion. So in relationship to making even just 1 millionth of a gram of antimatter. So let's talk about the energy scale. We have E equals mc squared. If this tiny little rectangle or a square here is 1 ton of TNT, then 1,000 tons of TNT is 1 kiloton. And we're pretty familiar with so the bombs that were produced had on order of about 30 kilotons, so that's 1 of these is equal to all of that. But then if we just take 1 gram of antimatter, this is a gram of gold in Canadian gold, actually, I was able to find a picture. But only 1 gram of antimatter would produce even more. So this is when people think, oh, these huge energy scales, how could we, have something that's so volatile and has so much energy? Well, to put it in perspective, the total amount of antimatter that we've ever produced today by accelerators is equal to about 1 billionth of a gram of antimatter, and if you put that into energy scales, that's less than what it would take to even boil a cup of coffee. Probably not even a droplet in the cup of coffee, or in your cup of tea. So with that, I'll let you ponder the units of scale.